Dear all, good afternoon. I am Rossella Berni, and we can start with this second webinar. And I begin with a very brief introduction. We speak about, in this introduction, about the Competence Center ARTES 4.0 and the macronode of University of Florence, which is one of the macronode involved in this Competence Center. 6 departments of the University of Florence are involved in the Competence Center activities, and all these 6 departments play a crucial role around business, industrial, engineering field, computer science, statistics, mathematics, and so on. But we are all involved in these macro nodes. So this webinar is a webinar number 2 with general title Statistics and Engineering in the European Context, and is organized by the Department of Statistics, Computer Science and Application, Giuseppe Parenti, DISIA. I am Rossella Berni, and with me are involved in these activities of the department within the macronode and also within the Competence Center, my colleagues Leonardo Grilli, Fabrizio Cipollini, Andrea Marino, and Alessandro Magrini. The Department of Statistics is for the second time, and for the next 5 years, for the second time, Department of Excellence. And I am glad of this, we won this, for the second time, this competition at national level, and are affiliated to the department 3 research centers. The Inter-University Center of Steering, Design, Quality and Reliability. And I would like to point out that within and with this center, we organized in 2020 a conference in which the speaker of today was invited. So, and in this context, we are organized, and I hope, will organize some events in order and always to connect statistics with engineering. The second research center is in the interdepartment Florence Center for Data Science, and the third is a competence center in cybersecurity. In this department, there are many expertises and activities in the perspective of 4.0 industry. And above all, sorry, but this is my research topics for in the industrial and technological fields in order to perform robust process optimization through DOE, through computer simulation and computer experiments. But also many colleagues and also some new researchers are going to study for industry 4.0, for example, for the efficiency evaluation, for economic evaluation, decision, data science, advanced statistical methods and modeling, predictive modeling and machine learning, statistics for business analytics. So I am very proud, and I think also my colleagues that are here with me now, to say that the statistical department and computer science and application is a very crucial for the next 5 years in order to solve complex problem with also complex data and data science. So we can start with the introduction of the webinar of today, 17th of February 2023. The speaker of today is Dr. Nikolaus Haselgruber, and I would like to thank, first of all, Nikolaus Haselgruber for being here, for accepting my invitation, and also because with Nicolaus, I share many times and many events in the ENBIS, the European Network for Business Industrial Statistics. We are together members of this association, in which we share also the some events, and we organize it together some events. Dr. Haselgruber has obtained a master's degree in statistics at the Johannes Kepler University of Linz in 2001, and currently is founder and the Chief Executive Officer of CIS Consulting in Industrial Statistics in Austria. He had many projects, is a partner in many development projects, and one of the last, and among the others, the project Virtual Stretch Analysis and Stochastic Drive Simulation of Commercial Vehicles based on electronic map data. Many publications, among them on Quality and Reliability Engineering International Journal, or in the Austrian Journal of the Journal of the Austrian Statistical Society, and he was invited in many scientific talks. The main topics of these talks are related to reliability and maintenance, because Dr. Haselgruber is expertise in these specific key fields, and in fact, he took many lecturers to the University of Vienna, University of Graz, in many universities about reliability, statistics, and management. He also contributed to organize conferences and invited sessions. And also he was, and he is co-inventor of several patents, always in reliability, maintenance, and optimization of technical systems. So we can start with the webinar. The specific title is The Role of Statistical Method in Problem-Solving Processes. I would like to give the possibility to present to Nicolaus, and also I would like to thank all the attendants for being here. Thank you, and we can hear Nicolaus and his talk. Thanks.
Yeah, thank you, Rosella, for your kind introduction and for the invitation to being here today. First of all, can you see my screen? Yes, okay. So the topic of my talk today is about the role of statistical methods in problem-solving processes. As Rosella already said, I have been working for a long time in the area of reliability engineering, and reliability engineering is, so to say, tightly connected with failures and problems, and of course with the need to solve them in a strategic way and in an effective way. And the point is that the problem solving itself is not a very typical scientific discipline, but it's rather a more or less a field where several disciplines are put together. And interdisciplinarity is very important to come to the target and to solve a problem. However, I just want to start with a quote of Einstein, who said, we cannot solve our problems in the same thinking we used when we created them. So it should be simply a kind of motivation to make a step back, to look at some thing from another position, to simply allow an open mind set to think about solutions which were not in focus so far, etc., in order to fix problems effectively. And just a small example, you see here two cubes filled with points, and these are two images of the same cube. It's just a matter of a different view on the cube. And we see that while the left cube looks like a random pattern, if we change our position by 90 degrees, we see that the points are not randomly distributed in the cube, but they are allocated in inclined planes. And just that we should sometimes also switch our position and take different points of view on a problem. What I want to talk today about is first about some types of problems. How can we classify it? Then about the problem solving process itself. And I want to introduce the 8D report as one possibility to go into a strategic way to solve a problem. And then since this is more an organizational framework, I want to point out what could be the role of statistical methods in general within such a problem-solving process, and then talk about a few special things, also population versus sample, which is, in my point of view, a very crucial aspect in problem solving. And I want to show a small case study and summarize the results. This would be my plan for the next half an hour. And first, what is a problem at all? So I looked in the dictionary for a definition, and the dictionary says maybe a problem is something which is difficult to understand and it needs a solution, basically. And this is what we are thinking about, and this is also, I think, what fits quite well into my thinking about what the problem is. And if we face such a problem, then the question is, what are triggers of the solving process? So what has to happen that we should enter a problem solving process? So either something should be improved. For example, in the last years, we have seen, at least this has been observed in Austria, maybe also in other countries, that people were not very satisfied with government's troubleshooting competence. So a problem which should be improved, maybe. Or another one, something has been found to go in the wrong way, and we want to correct it. For example, we see the waste of fossil energies, fossil resources is very high, and if we do not change anything, then at some point we will get the problem. Or something went more or less suddenly bad and should be corrected. For example, we have identified in a series production a product failure suddenly, and we need to react and we need to correct and to fix it. So such activities where we have a kind of a process, then something happens, which can happen either fast, suddenly, or also step by step. So something changes or something needs to be fixed or corrected. Then I thought about problem types, and I did a web search which is non-exclusive or non-complete. It's just what Google put out when on the first page when I searched for problem types. And what we see are several very different sources, and we see mostly 3 to 4 classes, and they all are very similar. They go from simple to complex or to chaotic, more or less. There is also a one which claims for simplicable, and this has 14 categories which are not in a certain order, or are, in my point of view, not disjoint or whatever. So so there is a lot of different ideas in this field, but I was not satisfied because I did not find any advantage to me. So I thought about a a slightly different and much simpler classification, and therefore I say also this is a subjective classification, because this is just a kind of a personal sorting of problem types. And I could imagine to split the problems into a kind of large scale and small scale problems, where I see a large scale problem is something where many persons or many individuals are concerned, and there is a need of a global commitment to make a solution. And also typically these problems cannot be solved by one action, but it needs to reach a sustainable long-term solution. We need maybe many small iteration steps, and only in small steps we can solve such problems. And other problems are small scale problems, where we have typically a defined risk population, and we have the decision making somehow under control. We can say, well, if this organization wants to solve the problem and the management is willing to do this, then this can happen. And typically large scale problems which we faced in the last decades maybe is the global warming, global diseases, malnutrition, the pandemic, terrorism, but also the digital revolution, and other things where a big variety and the big set of individuals are concerned. And if we want to solve this such a large scale problem, of course, it is not possible to do it as a single person. Of course, the involvement of an entire society is, or at least of entire organizations, is required. And I want to cite at this point Hans Rosling. I don't know whether you know them. In my point of view, it was one of the great problem solvers. And he claimed in his book Factfulness for the fight against ignorance. He said people need to be persuaded that there are problems where everyone is concerned with. And it's also very important to have a fact-based communication, but also a receiver-oriented communication. We need to transport results in a way that the concerned individuals are able to understand what is the topic. And of course, if we are talking about solving such problems, we cannot use only one method, but we need, of course, an ensemble of different methods for different steps and different topics in. Here I have one example which is taken out from the page Gapminder. I don't know who knows the Gapminder, which was an initiative of Hans Rosling I mentioned before, this is a very nice website which provides us with a lot of interesting data about large-scale problems. And what we see here is an image, a bubble chart, where we have the income per person. On the x-axis, we have the life expectancy in years on the y-axis, and we have one bubble for each country, and the size of the bubble corresponds to the population of the country. And we see, first of all, that we have somehow a relation between the income and the life expectancy. And we see also that the yellow points are mainly here up to the right, and the blue and the red points are up here down to the lower area. And this corresponds to the different areas in the world. And this was the situation in 1922. And if we now go 100 years into the future, so to say, to the present, then we are in 2022, and we see that things changed. first of all, the bubbles are getting larger. We had 2 billion people on Earth 100 years ago. Now we have 8 billion, and we see also that the overall level raised of life expectancy and so on. So this is a very nice thing which should be taken into account. Another example is about global warming, where statistical models have been used very effectively to simulate scenarios. What would happen if we would more or less change our habits and our living style? So what should have been, what must have done in order to keep the or stop the warming and keep the temperature on a constant level, or what would happen if we would do nothing? And you see also that what is the consequence in terms of additional temperature in the next decades. Of course, it is important if we look at such graphs and communicate such information. What are the assumptions behind the scenarios? So there is also a citation of a very good paper with where this information is taken out, and this is of course important to communicate. So this is just a very brief view on that, what I call large scale problems, and I want now to focus on small scale problems, which is typically, for example, we have a failure in a technical system and we need to remove it, or we have observed an accident and we want to find out the root cause. We want to understand why did this accident happen, or we want to develop a new product and we have some requirements, for example, legal requirements, safety requirements, whatever. We want to ensure that the product will fulfill this. This is what we typically mean with a small scale problem. And now to solve and to attack such small scale problems, we should here, in my point of view, concentrate on the involvement of key experts, which means we do not need to incorporate the entire society, but we only would include in the task force, in the solving circle, the key people. But of course, it is important that we also have to persuade the leadership that we have a clear support, because without leadership, maybe the improvement won't be successful. Of course, also a fact-based communication is needed, and this is also what I have seen many times. It is important that within the team we need to establish an outright communication. It is absolutely mandatory that all the truth has to be discussed, and that nothing should be hidden or masked. It's important to define the problem thoroughly, and we need a kind of a clear problem solving strategy. And of course, together with the leadership, we need absolutely the commitment of the management that we can collect and generate the required data we need for the problem solving. So, as I said already, we need a good definition of what is our problem. So what is exactly the objective? How can we measure it? How can we reproduce it? How can we ensure a comparability of the data? If you remember, in the beginning of the COVID crisis, maybe every country had own rules they are even now as they are, but own rules of how to count the cases, and the comparability was not given at all, but people compared, of course, And so this was a first very big problem. And of course, it's easier on a small scale, but it is important not to forget that the data coming from different sources may be incomparable, and this can, of course, lead to wrong conclusions. Important is, what is the population we want to investigate? So what are the individuals, what is the set of individuals which can be affected by our problem? And what are the hypotheses to be investigated? And what do we need to test and to check this hypothesis? Do we have enough of the data? So is the quality and the quantity enough? And of course, time, budget, what are the competencies required, and what are the resources needed to manage this? And I want to present the tool. Maybe you know it, but I used it several times and it turned out to be useful, and therefore I thought I want to present it, which is called the 8D report. And the 8D report is, for example, has been standardized in the automotive industry. And it says what are the preconditions when it should be applied. First, a product failure has been observed. And second, prior to the failure, the product worked according to the specification, which means we have a situation which changed. Initially, it was okay, and suddenly something happened such that we do not fulfill the specification anymore, and this is the trigger in order to start a problem-solving process. And the 8D stands for 8 disciplines, so more or less for 8 steps which should be carried out. And one step, the first is we should set up the problem-solving team, then describe the problem, then define immediate measures, then identify the root causes, so what's really behind the problem, then plan corrective actions, then implement the corrective actions, and then verify the corrective actions, which means avoid that it will reoccur, and then of course appreciate the process result, which means implement the correction and also inform maybe the affected individuals. Of course, the steps are not sequential, but they are also to some extent parallel. Of course, first we need a team, but then we can start describing the problem and start to implementing first measures. For example, just imagine you have a series production and you notice a certain failure which stops the production, which causes high costs because all the supply chains queue up, and this is a very, very critical situation. So it can be required really to define an immediate measure in order to keep the entire, for example, production process alive. And parallel to this, the root cause analysis and so on should start. But the key message of this slide should be that the process steps are typically not purely sequential, of course. So this is just a small framework of the problem-solving process. And now is the question, what is the role of statistical methods? So what can statistical methods in principle provide in this process? First of all, they can provide a quantitative result. Not just only this is a problem or this is a big problem, but we can say the failure rate is 20%, or the survival probability should be 99%, but it is only 80. So a quantitative result. The next one, we can make an inferential statement with statistics. So we can say the result is hopefully valid for the entire population, not only for a few samples we have observed for, but we can draw a conclusion from the sample to an entire population. The next thing is we can provide a root cause effect description. So we can say, well, we have detected some influences of factors on response variables. We can say if we would change the diameter of the shaft, then we can reduce the problem by a certain percentage. And of course, we can make a statement about the uncertainty of our result. We can say, okay, we can provide a confidence interval, a prediction interval, and also say, look, depending on the natural process spread and on the sampling error, etc., we get this and that uncertainty of our result. And here we have an example. We are interested in the resilience of a roller bearing of a certain type, and we want to know whether the lifetime under a load of 3.7 kilonewton survives 150 hours. And the failure probability, so the probability that it fails before 150 hours, should be less than 1000 ppm. And we did, as we see in the left chart, we did some component tests, and we see that we have with increased stress, the lifetime decreases, of course, and we see also we have a certain natural spread in the data, and we can build a nice log-log linear model, and we can put a confidence area around it and a prediction area, and we can look at 3.7 kilonewton. This was the lowest tested level. And if we look at this position of stress, and we map the marginal distribution, which we see in the right chart, then we see, okay, this is the distribution. Here is 150 hours, and we see the probability mass below 150 hours is 8000 ppm, which is larger than the 1000 ppm, which says with this analysis we cannot confirm the required resilience. But of course, I mean, we did not observe any value smaller than that, but according to the shape of the distribution, we have to think about the countermeasures. And the point is, okay, what can we do? Either we can increase the accuracy of the model, maybe increase the sample size, but the sample size, of course, only reduces the confidence area, but does not, in general, not reduce the prediction error, because this is due to the natural process variability. So maybe it will be required to use a better bearing and to say, well, we need a bearing which has a higher resilience than that type we have investigated. So, in other words, statistics can provide a quantitative result in this point. But we should also know and be aware of what can statistical methods not provide. So, of course, this is not magic, what we are doing here. And there are also don'ts. They do not recognize if a sample data are not representative. So if we have a bad selection of probes, they do not automatically recognize a bad fit. They also do not provide symmetric results. So the rejection of the null hypothesis has not the same quality in the statement as not to reject the null hypothesis. And of course, they do not solve a problem per se. So to see what are the limits of statistical methods is, we have here another example, testing an electromechanical system which has multiple failure modes. And in the left chart, we just do not take care about the failure modes, but we just throw all into one box and consider them as the same failure mode, and just make a Weibull plot and linearization of the CDF of the Weibull distribution. And we see the fit is not bad. So we have a rather straight line trend, and we get a rather a flat slope. around 1, which means the risk to fail is rather constant over time, and we would have a very large spread of times to failure. But if we look more carefully to the same data and we find out, well, these are not all of the same failure mechanisms, but we have a kind of an infant mortality which provides some early failures, and we have a completely different type of wear out at higher lifetimes, and we are able to split them into 2 categories. Then we have these magenta points and the brown points, the wear out, and then suddenly the common distribution function provides us with the black line in the right chart, and this highlights that we have towards end of life a very strong wear out effect, and this is only because we have considered the failure modes correctly. So this is a very, in my point of view, a very important thing, because the identification of the failure mechanism, of course, has an impact on the problem solving strategy. If we have an infant mortality, which, for example, comes from a bad assembly or production process, we need a completely different problem solving strategy as if we would observe and identify an aging problem, which means the design is maybe not okay. And a very important item in this aspect is the topic of population and sample, which means the population is, of course, the set of all individuals potentially affected by the problem, and the sample is the subset out of the population which we analyze. And of course, if the population is small, then we can even make a complete survey and just use descriptive statistics. But in general, we will have to use a random sample or try to make a representative sample in order to make a statement about a small sample and then inference to the population, of course. And we should be careful because if the sample is not representative, then maybe we make a wrong conclusion. And I just have here an example from official numbers about Austrian economy. We see here 2 kind of pie charts. The left is about the enterprises, and that the number of, it's always the number in both charts we see the same number of employees, but in the left one it is split after enterprises. We see 95% of the enterprises have only 1 site, 3.6% have 2 sites, 1% has 3 to 9 sites, and only 0.2% have 10 or more sites. And if we look how the employees are distributed over these enterprises, then we see that only 50% work in the 95% of the enterprises with 1 site, but 22% work in enterprises with 10 or more sites, which are obvious the large enterprises, but they, of course, they only make 0.2% of all the enterprises. So the point is, are we interested in the analysis about companies or about employees? And this, of course, would change the selection strategy if we would draw a sample. But now I want to enter a case study. We look at an electromechanical vehicle component, and this component failed in the field. So we had a series defect, and it failed due to a short circuit, so electrical defect. And we see in this chart failure rate stratum lines. This means we have a production date, and for every production cohort, we see the failure rate, and the blue line sums up all the failures in the first year, and the orange line, the failures in the first 2 years. So this is the 12 month in service failure rate and the 24 month in service failure rate. Of course, we can observe the line only in a descriptive way for the blue line only for units which have already passed the first year, and the orange line, of course, only for units which have passed the first 2 years. And we see that the failure rate increased at the end of the year 2019, and the 1 year failure rate said that it stayed for at least 1.5 years at a similar level. And now we ask, okay, what is the problem and how can we fix it? And yeah, we apply the 8T report. So what are first the problem solving team? What are the required competencies? Warranty, quality, reliability, component design, electrical engineer, component supplier should be involved, as this is a supplied component, and we need also the assembly and the vehicle integration. What is exactly the problem? The problem definition: we see an increased frequency of short circuit in the field. The consequence is that we have a dramatic loss of drive power, so this is more or less a breakdown, but the problem is not safety critical. And the population are all the electric vehicles, vehicle models which have been produced between 2019 and now. We do not have any immediate countermeasure because we do not understand the problem at the moment. We do not know what should we do as a short term. But the production is not stopped because the failure rate, the 12 miss failure rate, is not that high, and so we can we go on in the problem solving process. One important method is a change point analysis. We want to figure out at which point the failure rate is likely to change. And if we look at the 12 miss failure rate, we see that the change point is at the end of 2019 to beginning 2020. This is the most likely change point. And if we look at the 24 miss failure rate, we see that the likely change point is at the July 2019, which is, if we jump back, so this change point is in the red line, recognized better than this change point, because of course this is not that long and the sample is small for the second change point, for the second phase. And also this is interesting that this change point is that there is recognized a change point. So to understand it better, what to do, we investigate the failure modes. And now this is again the orange curve of the 24 miss failure rate, and we see, okay, the jump is basically caused at the point where a new vehicle model has been introduced, and we see that most of the failures we have observed here, they are due to humidity at the electric connector. And we see that another point that from July 19 on, this is a smaller percentage, but we see that here we have observed broken solder joints, and we have found out that at this point the solder material has been changed. And we have, in addition, of course, a wide noise of other failures over the entire period. Now we apply another method, a fault tree analysis, in order to investigate to visualize what are the potential problems and how likely are the single root causes. So we see here different root causes, beginning from the component design that it is not robust. Maybe the diameter of the wire is wrong, or the load capability is bad, etc. And at the other end, we see the vehicle integration, that either the underfloor protection is not sufficient because of the humidity, or it has a leakage there, the protection, or the positioning of the component is bad. And we have investigated all the different potential root causes. We looked at process capability analysis. We did measurements and checked some and added some investigations, and finally we found out that there are maybe two different root causes left. And the point is that here we see the most critical one, and the point is that the vehicle manufacturer decided to not use the underfloor protection anymore in the new vehicle because for cost-saving reasons. And this was obviously not a good idea. And here we have the quantification of the fault tree, and we see, okay, the highest or most likely root cause is the underfloor protection. Therefore, we defined two countermeasures. The first one is we should improve this protection, of course, and go back to the previous design, which has to be adapted a little bit because the entire vehicle shape changed. This causes higher production costs, of course, but it turned out to be necessary. The implementation duration is 6 months because you need a supplier, you need contracts, you need verification. But the potential in failure rate reduction is roughly 80%. So basically, this must be done in order to bring down the failure rate again. But a second measure has to be defined about the sub-supplier to bring back the soldering process under control, and this also needs some development and implementation of statistical process control, and it shows a potential of 5% of reduction. And then how can we verify this? So we verify the underfloor protection in order to compare the actual design with the improved design. It's a very simple full factorial design with one replicate. But we also, the key point is we verify the improved against the actual design, because we want to show that the actual design fails, but for the same situation, the new design works. So of course, the verification means to show and to demonstrate that we make things better and that we prevent the critical position of humidity. And for the soldering process, we can also make a rig test, and we can test 70 solder joints under certain defined conditions in order to demonstrate that also the solder joint quality is sufficient again. So what are the conclusions? Problem solving processes needs basically interdisciplinary. It's important that several different experts work together and try to speak the same language. We need a commitment of the leadership, because we need some resources in order to collect data, to make measurements, to observe things. And we need, of course, an open-minded thinking. It's also very important to communicate the results in a correct way, not to make it more complicated as it is, and to bring it to the point, so to say. Of course, this only works if the data quality and also the data quantity is sufficient, because the sample errors can be large if the sample sizes are small, and thus not only the quality but also the data quantity is required. So in my point of view, the conclusion is that powerful statistical methods are available, but to apply them in an adequate way, this is our job, and then the problem solving process can be successful and effective. And then I have finally a few references which have been cited throughout the talk. And then I'm at the end of my talk. I thank you for your attention, and if you have any questions, of course I will be there too, and hopefully can answer them to your satisfaction.
Thanks, Thanks, Nicolaus, Dr. Gruber, for your talk. Very interesting. And in order also to open the discussion and question, and I really hope there are questions, but some comments, but also questions, because you open with your talk many issues. You are dealing with many issues usually arising when statistics and engineering are connected. For example, you speak about the involvement of key experts, but this is very huge problem, because and a very important key point, because also, for example, when we are planning a DOE, an experimental design for robust process optimization, but also for reliability, the involvement of key experts, but also the open mind, and the open mind must be by their engineering side, but also from the perspective of a statistician, because the open mind is for both the experts. Okay, and in this case, we have necessarily any irrelevant information are must for planning a very important and effective and efficiency experimental design. And in this case, I would like to remark your slide on fault tree analysis. So when you show the fault tree, and you also put among the causes the design not robust, component design not robust. So this is another very important key point, and this is not so in mind of engineer or also of statistician. We must take care that all issues in a system reliability or also in a product process are all key points are connected. This means that when we are dealing with quality, this means also to deal with reliability. And so when we are speaking about a robust design for a component, we also speak about a robust process in order to do a product quality, but also a product reliability. And this is this is very important when we are dealing with process and industrial engineering. The other thing is that the last step, the appreciation, I usually name it validation of results. And this is very important, because when we do and when we make a study applying statistics in the engineering industrial field, is also very important to do the last step, and explicitly the step to validate our results, the results obtained by statisticians, in order to control if these results are really effective and are really real for the process we are trying to improve or try to optimize. Because sometimes and in some situation we can risk to make only a mathematical exercise. So all the steps that you mention and that you list in these slides must be connected, starting from the first key point up to the last, in order to improve and in order to consider all the real problem that can be effectively present in your product or in your component or in your system reliability or in your process. So this is very, very interesting talk. And I think that sometimes some key points are not so taking into the consideration or into the adequate consideration. Thanks.
Yeah, so I thank you, Rosella, for your comment. I fully share what you said, and and some of the points like the open-minded thinking, it's not the phrase only on the slide, but it's mandatory. I had a project some years ago, and then I presented the first results, and then I was not allowed to present anything anymore in the company because they did not like the results. Because of course they were not nice, and they pointed out that it was a big problem, but they did not want to hear this. And a few years later, then the reality came back, of course, because series does not stop. And then the management has been changed, and then they come back and invited me again under new boundary conditions, so to say. And then the problem was much bigger because it already increased, but then we could solve it with yeah.
Thanks. Other questions? Really appreciated. No questions.
Hi, I'm Leonardo Brilli, University of Florence. I really appreciated your presentation because it makes clear the interrelationship between statisticians and engineers, because I say that statisticians always work in team. Actually, or at least in principle, a statistician make an application has to work with some expert, or at least has to read books or papers to have a knowledge of the subject. And so this approach makes it clear. And my specific question is about uncertainty. I would like to know how uncertainty is typically represented, and how is it perceived by non-statisticians? Because, statisticians are always well focused on computing uncertainty, but sometimes this is difficult to communicate. So we can have a statistical test with a p-value. We can have a confidence interval, or we can make simulation, Monte Carlo simulation. So there are different ways to communicate uncertainty. So I would like to know from your experience, what is the most effective or the most commonly accepted in industry?
Mm-hmm. Yeah, so I can understand your question very well. It's indeed difficult. But I mean, if we talk about uncertainty, I think we have to distinguish between, so to say, the sample error, which is basically the statistical uncertainty, which we have under control, in a sense that we can say, well, we know the probability theory, we know the consistency of the estimates, and so on. You know, the square root of the sample size is typically in the denominator of the interval, and so this uncertainty we have under control. But at sometimes we have much higher uncertainty, which is due to the knowledge about the situation, and all, so to say, we do not know what we not know.
Yeah,
this is sometimes the larger uncertainty, and we have to be careful in the communication that sometimes we only communicate the statistical uncertainty, because this is what we can easily quantify. But this does not mean that there is no additional uncertainty. So this is the first thing which we should be aware of. But the second thing regarding how to communicate it, I try to explain my clients, look, the confidence interval or the measure of uncertainty, this is nothing else than a safety belt for you, because you want to make a reliable statement. You want to make a statement where others can rely on, can say, well, this holds. And you cannot make a reliable statement if you say, well, 50-50, it will be true or not. This does not work. And therefore, so I try to motivate why we communicate confidence bound, for example. And in addition, in some companies, I already I established a communication that this is easier if it's, for example, one-sided. If in the reliability, we always want to make a statement about the failure rate, and we are only interested in the upper bound, because if it's lower, then this is not critical. And so if for example, if we have an one-sided question, then we can, or in two companies, I managed to establish that we only talk about the 90% confidence bound anymore. We do not talk about the expected value, but we say we are pretty sure that the failure rate will be not larger than this value. In order to avoid misinterpretation and irritation of the consumers of the result.
Yeah. Okay. Thank you.
I have a question. Can I? I'm Fabrizio.
Hello.
Okay. Hi, Nicholas. I have a couple of questions. The first one, according to your presentation, I feel that the relationship between you and the company requiring your work are crucial in order to make your job done in some sense. The question is, how taking 100 partitioning your time to say you have a pie of 100% time, how much time you are spending in connecting your relationship with, in some sense, with public relations, and how much time you are spending in technical issues?
Okay. This depends on the relationship with my companies, I have to say. I have some companies which I'm working for more than 10 years. And in these companies, I use the main, let's say, the main part for dealing with technical issues, understanding the problem, talking with the engineers. I really try to understand the problem also technically, which is not always easy because I'm not an engineer. But I try to read something and to understand also the opposite, so to say. But of course, in companies which are where I'm new to, I of course need much more time, at least half of the time, to let's say to get settled and to build confidence because you have to know sometimes the problems are that critical that this can be economically dangerous or the dangerous for a job position or whatever. So people can be quite fried or can be somehow very scared or careful also in sharing results, and you need to make them understandable that my job is not to doing anything political or whatever economical, but I just want to, I always say I want to bring light into the dark. I just want to make things clear and to use statistics for let's say de-escalation and make it objectivation. And of course, I also can say that this does not always work, and I do not. Some projects did stopped before they started, so to say, because this basic connection has not been established. This also happens, of course, but yeah. But of course, I mean, so to say, the work split or the split of activities depends on the involvement in the past and how deep I'm in a process involved already.
Okay, thank you.
Thanks. Other question? Right.
Good evening, Dr. Haselburger. Thank you very much for this really interesting and useful talk. I have just a curiosity, a specific question related to your case study. In the statistical methods you have presented, you describe it briefly also the method of competing risks.
Yeah.
Okay, when we have different failure modes. My question is, if I'm not wrong, you are dealing also with competing risk in your case study. Is that true?
Yes.
Okay, and so did you maybe apply some reliability models for competitive risk in this specific case study or similar, or?
Yeah, in this specific case study, I did it not because the point is that here the time of the failure occurrence was very hard to detect. Because if I would like to apply a kind of a like I did it in the example before, a viable analysis or something like this, or considering competing risks, I would need the exact time to failures, and the point is that here this failure rate analysis is more on a global level of the vehicle. It just counts the failures occurred in a certain time interval, and this is easier to manage. And in this point, it was obviously clear that that the one with the humidity, the problem was so large, and it was also the root cause was immediately clear, because at the point when this jumped up, there was a design change, and they simply that they had a cost reduction program, and they thought they can leave this protection away, and the point was that this was not a good idea. And it was not the question about what is the expected lifetime. It's all people which saw this graph said, well, we need immediately come back to the old solution. This was clear very soon. And the other thing was that the thing with the solder joints, the broken solder joints, which are these yellow bars, this was a smaller problem from the order of magnitude. And here we did in fact a viable analysis, but we used this also then for the verification. But this was then again a single failure mechanism again. So we had no competing risks analysis, classical competing risk in this specific application.
Okay, thank you very much.
Thanks again to Dr. Haselgruber, to all of the attendants. Other questions? No. Nicolaus, many thanks again for accepting this invitation for the talks, very interesting, and to all the attendants, and I would like to close the webinar and the connection. So many thanks to all of you. Bye-bye.
Thank you. Bye.